this video, we're going to derive the formula for the sum of the geometric series. So this is actually the example that we had of 1 over 2 to the n minus 1, but this is just a little bit more general. So we're allowing now there to be a first term. A is called the leading term or the first term. And R is called the common ratio. So as you saw from our problem with the 1 over 2 to the k, it would have been a case where A was 1 and R was 1/2, right? Just this. Two to the n minus 1. So really we're thinking of this as 1/2 to the n minus 1. So what we need to do is, this is actually a really it's a pretty common form. It's a very nice form, and it's something where we can come up with the sum with just a little bit of work. Okay, so let's write down a couple things. So in other words, what I want to do, let's remind ourselves what we want to do. I want to find the nth partial sum and take the limit as n goes to infinity of that nth partial sum. Okay? And I want to do it with this general A and R. Okay, so let's see. If I write down what the nth partial sum is, this is A plus AR plus AR squared plus AR cubed to the nth term, which should be AR to the n, right? So now there's a trick to do this. Of course there is. But the trick is to realize that the form of it is, of course, that you have a multiple of R is going up. So what happens if I take this same Sn and I multiply every term by R and multiply it through? Now notice that I can do that because this is a finite sum. It's just up to n. So I can multiply everything here by R. Fine. But I'm knowing what I want to do, which is to make crap cancel out. I'm going to write it moved over 1. Right? AR to the n plus 1. So that's the trick. Okay? Oh, you know what? I screwed up slightly because the nth partial sum would be n minus 1 because we started from n equals, yeah, all right. So let me just fix that for you. Okay, that's actually correct. The same deal, right? But the nth term is n minus 1, not AR to the n. By the way, some books have it as AR to the n starting from n equals 0. So be aware of that. That's why I screw up sometimes. But I'm trying to be consistent with your book, which always likes to start this from n equals 1. We'll talk about that more later. Anyhow, so I've got these two things, and the idea is, why don't I subtract the second equation from the first? Right? I'm going to subtract the second equation from the first. So that means I gotta, all these become minuses. And then all these terms are canceling out because they're the same. So what you're left with is Sn minus Rsn equals A plus, minus AR to the n. Okay? So then I want to solve for Sn. So I can take Sn out here. I get Sn times 1 minus R equals A minus AR to the n. Divide through. All right, hold up. I can divide through as long as I'm not dividing by 0. So at this point, I'm going to do pointing out the fact that R is not equal to 1. We can go back and figure out what happens when R equals 1. Of course, you can see immediately that's not good because you're adding A. That's going to diverge. But we'll do that properly. In this case, I can't divide if it's equal to 1. So I'm just going to, for the purposes of my calculation, just take it not equal to 1 for right now. All right, so here's my Sn. Now is my problem. I want to take the limit of this as n goes to infinity. I'm going to get rid of this so I have space. I'm just going to put this up here. Limit as n goes to infinity of Sn is then going to be the limit as n goes to infinity of a minus a r to the n over 1 minus r. Now, what now? Right? There's only one n left in the problem. It's up here. So this is equal to a minus a times the limit as n goes to infinity of r to the n over 1 minus r. But what is the limit as n goes to infinity of 1 over of r to the n? We did that last week, right? With like a whole video on it for different values of r. But this is what we got for checking all those different values of r. Limit was 0 for absolute value of r less than 1, 1 for absolute value of r equal to 1, and then this diverges for all the others. Okay, so this tells me something about this limit. First of all, we don't care about r equals 1. We have to do that separate, right? Because we didn't want to divide by 0. So I don't have to worry about that. I mean, I have to do it later, but I'm not doing it right now. If r is less than 1, then this goes to 0. So if this part goes to 0, I end up with a over 1 minus r. And that is the sum. Okay? But that's only true if r is between -1 and 1. Right? Otherwise, we're here, this diverges, and if this diverges, the whole thing diverges. So this diverges otherwise. Okay. Now I do have this question of what's it going to do for r equal 1. And I have to take care of that before I can write down my rule. Okay, but it's easy to think about that. If r equals 1, then what do I have? N equals 1 to infinity of a. So this is just adding a to itself an infinite number of times, right? So this is like the limit as n goes to infinity of n times a. So this is going to be infinity. There's nothing, no matter how small a is, eventually it's going to go up to infinity. It turns out you can also do r equals -1, but here you can already say that that's no use when r equals -1. If you do r equals -1, you'll get a minus a plus a minus a. So that also does not work. So what we actually have is diverges for r equals 1. It diverges for r equals -1. And so we can put that there like that. And let me write that here. It's equal to a over 1 minus r if absolute value of r is less than 1. And diverges if absolute value of r is greater than or equal to 1. So this is actually the sum of your geometric series. Now, it's nice to know where that formula comes from, so which is why I always like to go through it. I will not ask you to reproduce the proof, though. I just need for you to understand how to the formula and to use the formula. So we'll do, in another video, we'll do some other examples, but I just want to look briefly at the one we had, right? We had 1 over 2 to the n minus 1, and starting from 1 to infinity. And so if I looked at this, I have 1 plus 1/2 plus 1/4, etc. So A is 1 and R is 1/2. And if I put that into my formula, of course I know 1/2 is between -1 and 1, so I'm good here. I got 1 over 1 minus 1/2. It does, in fact, go to 2 like we saw on the GeoGebra worksheet.